All right. I hope I'm still sharing this screen over there. This screen over here. Sorry, I just had a technical difficulty over here on my side. So I think, yeah, we were continuing with our Openmp Basics. Okay, so just to get back a bit and to see what we're going to do, again, Openmp is something that we program into our C code and that the compiler picks up. So it's a compiler optimization strategy, right? So you need an Openmp enabled compiler, and this should be fine if you follow the Sigmund installation that was part of week 2. What we're going to cover, the work that we're going to cover, the topics that we're going to cover today is the Openmp Basics, some notes on shared variables and private variables, and then also how can we lessen our workload, how can we parallelize things in the code using what we call loop constructs. But all these are going to become clear when we go through the lectures. It's all based on this textbook, reference 11, that you guys should have on the shared FTP server. And it's covered in pages 228 to 309, and also in these references 16, 17, and 18. Okay, so let's dive in with the Openmp Basics. So remember what we're doing. What we are doing is our goal is to write software that we can run efficiently on a server or a cluster that might consist of a couple of nodes. So this is node 1, node 2, and there's 2 physical separate nodes, and on a node we might have a CPU that contains various processing cores, here core 1 and core 2. Now with Openmp, the goal with Openmp is to do the acceleration on a node, because remember, when we distribute the work between the nodes, we've seen in the previous lectures, we can use something like MPI, which is a message passing interface for intranode communication. But internode communication, we're going to see if we can parallelize the software using Openmp or in next week's lecture, GPU acceleration. Okay, so again, Openmp is a flexible tool for incrementally parallelizing a shared memory-based code. So it operates on the particular node. Okay, just to summarize the structure of the architecture that Openmp targets. This is again just a different view of the previous slide. We have a node. This node might consist of 2 sockets, CPUs, and inside each of these sockets there's various cores. Here, for example, each socket contains 12 cores. So in total there's 24 cores that we have over here, and we would like to benefit from the fact that on this node we have 1 block of memory, right? And how can we benefit from this shared memory architecture? Because in something like MPI, we saw that each process had to have its own distinct addressing space, which makes it possible, obviously, for intranode communication. But on a node, we have 1 bit of memory, 1 piece of RAM, right? And we really want to make full use of this shared memory environment. And that's where Openmp comes in. So how are we going to do that? So just to recap, the Openmp goal is we want to run 1 process on this node, and then inside of this 1 process, we like to use this concept of threading so that each of the various cores are utilized to its full potential in order to accelerate the code even more. All right, so the Openmp programming model is based on this fork join principle. So what happens is we have an original process that runs the code sequentially. It runs the code sequentially, and then it is issued a fork, right? So it forks into various threads, and then in this region we have parallel execution. So now, if we in a clever way distribute the workload, each thread can tackle a bit of the problem, and we get a speed up. Hopefully we get a speed up. Inside of a threaded region, a parallel region, you can do a fork again. So you can have these nested forks, which is wonderful. But at the end of this parallel region, everything comes together again, and these threads join to form the sequential single process. And then afterwards, you can have another parallel region where the threads are again forked and then joins again at the end. So this fork join model is the idea or the central theme in which OpenMP tackles or approaches the parallelization paradigm. So again, yeah, as we said here, the original process splits or forks into various threads. These threads joins again at the end of that parallel region to form a single process, and so on. Okay, so in the parallel region, the work is distributed between the threads using a work sharing construct. We're going to see how that works later when we look at the loop sharing one. But the idea of a work sharing construct is that it divides the available parallelism over the threads. So in the parallel region, the threads have access to all that was computed so far. So the idea is in the parallel region that these threads can have access to a lot of the shared variables. So you don't have to duplicate this or send them amongst each other with dedicated communication calls like we saw in MPI. And that communication overhead is also mitigated in a way. Okay, so as I said, what is the benefit of something like this? We're going to mitigate some of the inter-process communication. Right, so just to summarize this bit, OpenMP uses teams of threads and inside a parallel region. Then this is done using this fork join model. Inside of this parallel region, the threads distribute the work amongst themselves, and they can also have access to shared data. However, some things is better suited to be unique to each of the threads, and that's where private data comes in, and we're going to see how that works a bit later. One of the big benefits of using this threaded OpenMP approach is that there's little communication overhead as compared to MPI in the parallel region. But remember, for intra-nodes, so if we have two physically separate nodes, there's no way you can use OpenMP to benefit from that architecture. Then you would first need to use MPI to distribute the processes to each of the various nodes. But on a node, we can look at an OpenMP implementation inside of the process to benefit from it, to improve the parallelization even further. Okay, so what is an example of what an OpenMP program looks like? Well, it looks a bit like this. It's just a C code. So OpenMP is handled by extensions to your regular compiler, which is done by adding an option to your command line. Okay, so we call the compiler GCC in this instance, create an object file called foo, and this is my C code foo.c, and I pass it this option, -f OpenMP. And this is the compiler option that's passed so that the compiler knows that foo.c contains OpenMP compiler directives. What do these look like? Well, they look like this. It's these hashtag pragma statements, which speaks to the compiler. And then I have a list of them that I can use. OMP parallel is one where I define my parallel region. So this is my parallel region. And I also have various runtime libraries that I gain access to, like OMP get thread num, gets the number of the thread inside of the parallel region. And I can also get the total number of threads over here. OMP get num threads. So how many threads am I using? And then to get access to all of this, you need to include, like we do with MPI, this header file, include omp.h, gives us access to these. So this program, for example, I'll run and I'll upload that C program to our shared directory so you guys can have a look at it. But this program is executed as follows. Once I've compiled it successfully into something called omp.hello, maybe it's on Windows, so it gets an exe file at the back. I first have to tell the environment how many threads do I want. There's various ways in which we can do this. One of the easiest is to set an environment variable. Here we say export omp num threads equals 3, which tells me that I have 3 threads that I'm going to use, or tells the process I can use up to 3 threads. and then I run it. And then previous example, I'm expecting this type of output. I am 0 of num threads 3. I am 1 of num threads 3. I am 2. So again, we get these indices. They are only valid inside of this parallel region. After this parallel region, no more threads exist. Well, only a single thread exists, typically the master thread, which is thread ID number 0. But there's also a different way in which to set the number of threads that the program might use, and that is during program execution or during runtime. So you can call this function OMP set num threads, and I give it the number here, 3, to set the number of threads dynamically at program execution. So, okay, so just to recap about that program, we need this omp.h header file so that we can get access to the OMP runtime library and also some of the directives. We can create our parallel region using these pragma statements, which tells the compiler what are we going to do. And then inside of the parallel region, we follow what we call the single program multiple data model. So that is, all the threads are executing exactly the same segment of code. So you're going to have to think about how we structure our routines in this region in order to benefit fully from this parallel environment. Or we need to make sure that all the threads get something to do so that the work is distributed and we get a speed up. Okay. As we said, one of the big benefits of Openmp is the fact that the variables can be shared. But there are certain rules about that. And understanding when a variable is shared, when it's not shared, when it's private, things like that, that is critical for effective implementation of Openmp code. So let's look at it. It's not very difficult if you take certain rules into account. So a variable in an Openmp bit of C code or whatever, Fortran code or Python or whatever for that matter, can have two states. It's either shared or it is private. And we call that its context in the parallel environment. So shared context variables are variables that are visible to all threads that are running in associated parallel regions. So if we have a parallel region, which looks like this is a parallel region, all the variables, and the idea with shared variables is that all the threads have access to those variables. That makes things very memory efficient, but also very dangerous. Now, care should be taken regarding the access to these variables to avoid a race condition. So what is a race condition? A race condition occurs when two threads tries to access the same memory without some proper synchronization. So without making turns to do that responsibly. So this can cause the program to produce non-deterministic results in parallel mode. So who wrote first? Who did what? It's a difficult situation that we want to avoid. So shared variables, awesome in terms of memory, very efficient. You only need one, but also a bit dangerous because we need to avoid race conditions. And then we have private context variables, where each variable is hidden from other threads. Okay, so essentially every thread has its own private copy of the variable, and modifications made by a thread to its copy is not visible to the other threads. So it's almost like a MPI type of, similar to MPI, where each of the variables gets its own distinct addressing space in memory. Okay, in some cases this is needed, as we will see a bit later. So when is a variable what? When is it shared and when is it private? There are certain default states, so default contexts, that's determined by the following rule. So variables with static storage, so if you have a static variable in your code, they are shared by default. Variables that's dynamically allocated, so when you apply a malloc to allocate some array or something, those variables are shared by default. Variables with automatic storage duration that are declared inside of a parallel region are private. So if you declare a variable inside of a parallel region, it is private. Variables in heap allocated memory are shared. So these are all essentially also all the dynamically allocated variables. All variables defined outside of a parallel construct becomes shared when the parallel region is encountered, unless they are explicitly cast to being private. We'll look at some code to see how this works. And then loop iteration variables inside of parallel loops, inside of parallel regions are private by default. So quite a mouthful of things to remember. Let's look at some code, which should make it a bit easier. This is just general code. Let's say I didn't include all the header stuff here, but I have a variable here. This is a global. Then I start my program over here, void main. I have some input arguments. I end my program over here. I have my main program, okay? And then at the bottom, I have a function called foo. So in my main program, let's look at these variables, E1, the input arguments, and I. These variables, remember, where's my parallel region? There's a parallel region over here, a governing parallel region. It ends over here. And then I also have embedded inside of it two other parallel regions, an pragma OMP4 and an OMP parallel region over here. We're going to look at that keyword 4. Don't worry about it now, but what we have in this program is a general Openmp parallel region, and inside of it, two distinct ones. Now we want to figure out these variables around it and inside of it. Are they shared or are they private? So let's look at the first ones over there, the E1, the I, and the input argument. These variables are shared. Why? Because firstly, they are defined outside of the parallel construct. So when the parallel construct is encountered, they become shared. All the threads have access to them. This is a dynamically allocated variable, P, and this is also shared. Now we're inside of the parallel region. So the variables B becomes private because variables with automatic storage duration that are declared inside of a parallel region are automatically cast being private. So that is it. Each thread has its own copy of B. I is a loop iteration variable, and this is private by default. What now about this variable B, which was private in the overarching parallel region, but inside of this one, we now fork this parallel region again, and we use this B. Inside of the second parallel region, B will be shared, because for that parallel region, the fact that B stemmed from the outside is such that all variables defined outside of this parallel region will become shared when shared by default. And what about this function, these variables? So variables with automatic storage duration that are declared inside of a parallel region are private. And I, this variable I that we pass to the function, is also a loop iteration variable. So it's regarded as being private. Okay. And also that C that is defined here inside of the function. This is a private variable because it is declared inside of this embedded parallel region. A bit of a tricky at first, perhaps, but if you just remember the first 5 default situations, then it shouldn't be difficult to see when a variable is private and when it is shared when we work with Openmp. What about this one? This declaration called first private. So in Openmp, we call this a clause. So we say that P, the variable P, which is this dynamically allocated variable that would have been shared by default, should be regarded as being private. Not just private, first private. So what does this mean? So in Openmp, there's various clauses that we can use. Private, which says that the variables in the list are private to each thread. So over here, this P can also be replaced by a list of variables separated by commas. It's not just one variable. We can add multiples to to it if we want to. But and first private means that it's this very similar to private. The only difference is that the private variable is initialized by the original value of the variable when the parallel construct is encountered. So it's also a bit of a thing to think about when we work with Openmp is how are the shared variables that comes in regarded, or how are they initialized? And using things like first private, last private, and so on, you can specify that initialization a little bit. Okay. All right. Now, so now we know how to create an Openmp program in C. We know how to declare the parallel region, and we also know how to declare the variables as being private or shared. But what we need to look at now is how can we distribute the work between these various threads so that they all get something to do, and we benefit from speed up. So we're going to look at something called functional parallelism. So that is sharing the workload between the threads. So again, just to recap, our parallel region looks something like this. We have a pragma statement which tells the compiler that this is an Openmp parallel region. And here's a very simple, nothing magic happens inside of this parallel region at the top here. I only say that each thread will just print out a message saying I'm thread number something of total number of threads. And this, we say that this is an instance of a SPMD, single program multiple data model. So all the threads execute the same segment of code. But we need to figure out now, how are we going to divide the workload between the threads? So let's just say we need to calculate some result. And this result is the sum of three functions. So some function a, f, g, and h applied to the input variable x. And we need to calculate the results. And let's say that each of these functions takes some finite time, some time to solve. So ideally, we want to distribute. We want 3 threads, and each thread computes one of those functions. So how are we going to do this in Openmp? So it might look something like this. So here's now an example of how this work is distributed, how we have a single program, but we have multiple threads working on multiple bits of the data. So we have a parallel region, and inside of it, we first get the thread's number using OMP get thread num, that runtime library. And then depending on the thread number, it executes one of the functions. So if the number is 0, it can execute f. If its number is 1, that thread will calculate the result of this function g, and if it's thread number 2, it'll calculate this thread number number h. This function number h. And then at the end of the parallel region, the results can just be combined. Okay, so the result is f result plus g result plus h result. And if these variables I would typically have can typically be declared outside of this region, so it doesn't matter, but because each thread just accesses a distinct one at a time. So something that we will look at later is loop parallelism. This is a bit of a look ahead. Loop parallelism is a very common type. We've got a loop. Inside the loop, some work has to be done. How can we split the loop iterations between different processing threads or processes in order to benefit from each one doing a bit of the iterations of that loop? So Openmp has a very easy built-in mechanism for this. We call it, it's part of its work sharing constructs, which we will look at later. And you can specify it using something called something like this, as shown on the bottom right hand, where you say that you're going to create a parallel region, but this parallel region is going to be specifically the distribution of a for loop. And then this for loop is split between the threads so that all of the iterations are done very nicely, but it has some assumptions. The loop iteration calculations has to be distinct, for example. So do they rely on each other? If they do, that's not a good thing. You need to rewrite your loop so that each loop iteration is independent of another one. But again, we'll look at that a bit later. So in order to explain how OpenMP does something, I took an example, and this example is something that looks like this. So the goal of it is to calculate the value of pi, and we're going to use some numerical integration to do that. The example is based on what I found in this reference 16 over there, where we can use this integral, this definite integral from 0 to 1 of 4 divided by 1 plus x squared. And that integral, if you work it out, actually gives you the value of pi. On the right-hand side, I just I graphically plot that function for you. No? It's coming from 4 on the y-axis downwards, and the x-axis obviously runs from 0 to 1. So what are we doing with the integration? Just to take you guys back to first year, we can also divide it up into these little blocks, and we're calculating the area under that curve. No? That's all we're doing with integration. We're calculating the area under that curve between the interval 0 and 1. And to do that, we can use a Riemann sum. So we have a summation over here where we have these indices. I start from 0 to n. N is my number of blocks over here, these rectangles. I calculate the value of f. F is my function, 4 over 1 plus x squared. I calculate this function at this interval xi. So xi is perhaps the taken at the center of each of these rectangles, and I times it by the distance, the length of that little rectangle, which is delta x. Okay, and if I calculate this Riemann sum, then I should get to pi. So how are we going to implement this using OpenMP parallelization? Well, firstly, let's just look at how can we do it using serial code. So this is a very simple example of to do things serially. Obviously, you need to declare your number of steps. So n, how many rectangles do I have? And some variable, it's my step size. I start my program over here. It's important that you note you don't always have to use these global variables. You can also you could have put them in here just as local variables to the main function, would I have preferred, but this is some code that I took from this reference 60. So anyway, so I need to declare some variables here. So I have I, which is my loop iteration variable. I have this value x, which is my essentially my x, my delta x name, pi, which is the result, and sum, which is an intermediate result that I'm going to store. So first thing is we need to initialize our step size. So the step size is just 1 divided by the number of steps. Then I loop between all of my rectangles, and I calculate x, which is my specific x position. And then I calculate my sum, which is just essentially the value of my integral of my function at that particular x intercept there, and I add them all together. So this for loop essentially implements this Riemann sum over there. I don't have to multiply each and every time by delta x. I just perform this over here, this is the sum of fx, and then after my for loop, I multiply with the step size, right? Just a little bit of added efficiency there. But you could have put this step size in here. There, it would have been just a bit inefficient. In any case, and then I can calculate the value of pi. So you can implement this, you can run it, and you can see that this works. Now, what our first approach is to solving the problem is a single SPMD model. So let's say that what we're going to do is we are going to store our sum, our Riemann sum. Let's say we have no tricks up our sleeve to sort out the fact that various threads should not overwrite each other's data, so to avoid a race condition. So what we might do is to say, okay, let each thread write its result in a unique piece of memory. So let's rather declare this result variable sum to be an array of size num threads. So each little thread gets its own, let's say, unique piece of memory where it can store its results. So then the Riemann sum over here, which is now inside of the parallel region, that's the computing intensive part, is essentially just done so that the result of this sum is stored in this position ID, and position ID, or this ID, is just equal to the thread's number. Okay, so threads don't overwrite each other's variable. It's each other's variable, but I sacrifice something in that I now need more memory to do this. So, but it's my first approach. So this, as I said, is an example of single program, multiple data. We run the program, the same program on P processing elements, and P can be arbitrarily large. So that is P threads, right? And we use the rank of the thread to select between a set of tasks. So what should it calculate, and also where should it store the data? So if we look back, even our for loop here is split so that each thread calculates a unique part of this Riemann sum. So we split the work seemingly pretty equally between the threads. Okay, cool. So this pattern is very general and has been used for used to support most, if not all, the algorithm strategy patterns. So it's really an awesome work sharing pattern, and we use it a lot in MPI programs, as you guys have seen today. So we've implemented this now, and we're going to run it, and we're going to see what the results are if you use different numbers of threads. Okay, so this is what the results were of this program, where I compiled it. I'll give you this C code as well in this week's set of resources, and you will see. You can try it on your computer, but what I found is that if I used 1, 2, 3, and 4 threads, and I looked at the runtime, then with 1 threads, it ran at about 1.16 seconds on my computer. And then 2 threads, also 1.1, 3 threads, 1.19, and 4 threads, 1.18. So what is going on with this runtime? It's not scaling at all. Okay, so there's a problem. Something's not working well. And the reason why it's not working well is because now we've got to look a bit at a lower level on the computer, what's going on there. So we have this situation that we call false sharing. So what happens is when we have an array of variables, like we have this sum, we've declared it of dimension number of threads that we're going to use. In this example, number of threads is 4, for example, right? It'll sit on what we call a cache line. Now, remember, your computer has these hardware, these caches. A processor has a cache in order to mitigate the amount of the time it needs to pass variables in and out of RAM. So what happens is an array sits on one of these cache lines. And now, if it can happen that if we create or promote a scalar to an array like we did this sum, then the array elements are continuous in memory, okay? So they might share a cache line. So on one cache line, I have the bits of memory that is required by different numbers of threads, okay? So in one instance, hardware thread 0 is writing to the cache line in this area, but in the next instance, hardware thread 2 needs to access another bit of this cache line. Then the cache line has to be passed back to main memory and into the cache of this processor core, and this overhead, that is the sloshing back and forth of the cache lines, is causing this problem. So how can we overcome this problem? One way in which you can do this is to pad the arrays so that the elements you're using are stored on distinct cache lines. So here we only want sum 0 and maybe sum 1, and on this cache line we only want sum 2 and 3's data. So we can do it like this. So let's assume we have a 64-byte L1 cache line, and we can pad this sum array so that that each sum value is essentially in a different cache line. Okay, so we convert it to a two-dimensional array where we have the number of threads as the first dimension and this padding variable, which is 8, as the second dimension. It's 8 because sum is of type double, which is also 8 bytes. So 8 times 8 gives me this 64-byte L1 line. And now I just need to access in the second dimension, the 0 element. So it's like a dummy variable access. The only reason why I do this is to get this sum so that essentially on each of the cache lines, each bit of this two-dimensional vector gets stored in one line like this, right? And I don't have this back and forth passing so that each thread can gain access to some part of one cache line. Okay, so now that I pulled out my padding trick, what happens to the runtime? Oh, awesome. So I run it just by this small change, just change. All I did from comparing this example to the previous one is I just added this padding. And the run times improved quite dramatically. So it reduces from 1 second to about 0.2 seconds. And it decreases monotonically. Using 2 threads is faster than using 1 thread, 3 threads faster than 2 threads, 4 threads faster than 3 threads. So now my parallelization is starting to look a bit better. But this is quite a low level fix. Sure, you need to figure out how your cache lines look. You need to know what the L1 cache size is. It's not something very trivial. So we need to figure out. Is there perhaps a simpler way in which we can do this? And the nice thing is, yes, there is. So we can do this using Openmp work sharing constructs. So dedicated constructs in Openmp to avoid this type of situation. And everything is also, what I'm going to show you is based on this reference 16. So as I showed you in the previous slide, is Openmp has this internal support for working with loops amongst threads in a team. So I have my parallel region, hashtag pragma-omp parallel. Inside of it, I say that I want to parallelize this for loop. So I add this Openmp directive, hashtag pragma-omp for. It's called a loop construct. So remember, this variable I is made private to each thread by default, so we don't have to worry about that. And then inside of this for loop, we have this function called need stuff, or whatever I need to parallelize. Like we saw in our example, I'm going to calculate the area under our curve to find pi. So essentially, what the OMP4 does is it just very neatly distributes my workload and my memory in such a way, or access to memory by threads. It just schedules such that there is no race conditions and the work is divided equally. So it replaces a big chunk of code like this with something much more concise and elegant. Okay, and sometimes, like we saw in our pi example, there's this concept of a reduction. So what is a reduction? Reduction is you keep on adding a value to, you keep on adding something to one variable that is based on each of the loop iterations. So let's say, for example, we want to calculate the average of something, right? So I have this average variable and I add to it the value of this vector A. This is called a reduction, and various languages, parallel languages for that matter, has internal support for it. Okay, so in Openmp, we also have specific support for this reduction. And to do this, we use Openmp clause, which is in addition to specifying you have a parallel for loop, you say that you add at the end, you add this keyword reduction. You say, what do you want to do with your reduction? So if you look back at the previous example, this is a plus. So the operator is a plus, and on which variables should the reduction occur? Okay, in our case, we have this average variable. So inside of the parallel for the work sharing construct, what happens then, what Openmp does is a local copy for each of the variables that's mentioned in this reduction list. So average in this case, local copy is made of that, and it's initialized depending on the operator. So if it's a plus, it gets initialized to 0. Then the updates occur on the local copy by each of the threads. Because remember, one critical thing is we want to avoid the race conditions. So the local copies are then reduced into a single value and combined with the original global variable. So we get our reduction or summation. And but one critical thing, however, is that the variables in the list, so in this case, only the average, has to be shared in this enclosing parallel region, which is understandable. Okay, so our reduction operators looks like this. We have a plus, Openmp reduction operators that you can have access to. A plus, the initial value of the variables that you list will be 0. Multiplication, obviously, initial value cannot be 0 because then the whole situation will just be 0. So it's got to be initialized by 1. And also minus is also 0. And then you have this min and max reductions, which are also pretty cool. So let's get back to our pi calculation. How can we now use the Openmp loop construct to parallelize our serial implementation? And we also want to, another thing that we want to do as programmers is we don't want to rewrite things a lot. We want to keep things as simple as possible. So for this particular example, how can we make a minimum amount of changes to our serial code and convert it into a parallelized Openmp code? And this is what you add. So this is our serial code, and the red bits over there is just the Openmp statements. So again, at the top, I need to include openmp.h. Then I'm going to add my for loop in Openmp parallel region, which is the red over there. I am going to change my for loop or precede it with the OMP for statement or clause. And I'm going to say that we are working with a reduction over here. The variable into which the reduction results are residing is this sum variable. And it has to be shared by default that we saw, which it is, because it's declared at the top outside of this parallel region. The operator that I would like to apply to my sum is the plus, which we see in the brackets over here. So this is all I added to my serial implementation and in order to parallelize it. So let's look at the runtime results. And if I run that code using 1 to 4 threads, I see a dramatic improvement in time. So what is a bit interesting is why one thread is, oh, okay, no, because I'm still working with much more simplified code. I'm comparing this runtime results to that of the array padding method, when we converted the sum into an array, two-dimensional array, to sort out that. And because I have much simpler code, my runtime is also much simpler. My runtime for one thread is also much more efficient. And I see that my code scales, also scales quite nicely when I use more than one thread. So what's critical to remember, there's a lot of things associated with Openmp that we could not cover in this lecture, understandably, but there is a lot of resource material for it. If you look at online, there's the openmp.org website, which covers a lot about this standard, and also the textbook references that I gives much more strategies for applying Openmp to its fullest. So what I would like you guys to do for homework is I want you to write a hybrid MPI Openmp program that can efficiently perform a matrix vector product on a cluster that consists of multiple nodes with a shared addressing space. And I'd like you to go for this, and I want you to profile your code on the CHPC. That's all. Do that, please. Submit it in a report. Talk about your scaling, your implementation, the design, and submit it to GitHub. That's it. Here are the references that you guys can use. These are the additional references, 16, 17, and 18 that I added. Again, I want to point you to this openmp.org website, which has a number of very useful things to look at. And yeah, so, and I just want to acknowledge the following people for assistance and also support for this course. Thanks.